As the generators respond to changes in electrical load, a mechanical system of flyballs, valves, and oil pumps automatically adjust water flow to the turbine. Today, many older hydro stations have been modified to electronic controls or manual operation. Here at the dam in Brainerd, Minnesota, we get to experience lots of unmodified, century-old technology still in full operation. Hello, I'm your host Jason from Steam, Electricity, and Propulsion. The first thing we see when walking in the plant is a diesel-powered fire pump. A large building up on the hill used to be a paper factory which relied on these for fire protection. Here's a paper flow rate recorder for the fire pumps along with a second smaller diesel-powered pump. Beyond the diesel fire pumps, there are some generators spinning at 225 RPM. According to my tour guide, one of these generators came from an iron mine in Hibbing. It may have originally been a large synchronous motor used to power mining machinery before being converted into a hydroelectric generator. Dating back to the paper mill era is a steam-powered ram with a shaft-mounted grindstone that was used to turn wood into paper pulp. This generating unit no longer has automatic controls and its wicket gates are now operated manually. At night, when the operators are gone, they reduce the generator's power output so that if it should trip, it wouldn't run away. If the wicket gates were left wide open and the generator lost its electrical load, the unit could overspeed and suffer mechanical damage. With some struggle, this hand wheel can control the wicket gates, but it is usually controlled by this air motor. It can go either direction and drives the gates through a gearbox. The real highlight of this plant lies in the end of the powerhouse. Let's look at the rare mechanical governors. These 700 kilowatt generators run at 128.5 RPM and can produce 60 Hz power with 56 electromagnetic poles. While most hydro generators run from 90 to 240 RPM, this speed was likely chosen because the turbine was most efficient at this speed. To keep the speed constant with changing loads, there's a Woodward hydraulic governor. The other generators without governors can't automatically respond to changing loads. Their load is set manually and speed stays constant as a synchronized alternator is locked into the grid. If the turbine speed begins to change, centrifugal force causes the spinning flyballs to move inward or outward. Through a series of linkages, this movement shifts the small pilot valve. Rather than directing oil directly to the wicket gate actuator, the small pilot valve controls a larger hydraulic relay. The relay valve then directs high-pressure oil to the wicket gate power piston, causing the gates to open or close. As the power piston moves, a mechanical feedback linkage moves the small pilot valve back to its neutral position. This centers the pilot valve, causing the relay valve to return to its neutral position and stopping the movement of the wicket gates. The relay mechanism does not affect the position of the flyball linkage. The relay valve linkage connects to the opposite end of the rocker arm from the pilot valve, while the flyball rod connects in the middle. Here we can see the pilot valve mechanism responding as the load on the generator is adjusted. As the load adjustment knob is rotated, this cam limits how far the wicket gates can open. When the gate position is increased, lever number 55 moves downward, moving the small latch away from a catch on lever number 53. This allows the governor linkage to move farther, opening the gates. To set the governor's speed, this motor tightens or loosens the speeder spring through a system of gears. If the spring is tightened, the flyballs must spin faster to generate enough centrifugal force to overcome the force of the spring.
So right now this motor is hooked up to our relays. So when we push the button, it'll spin this automatically for 5 seconds to try and speed the generator up or slow it down. So it'll sync to the grid automatically.
On the power piston, a linkage feeds motion back into the governor. Visible here is the compensation mechanism designed to cause speed droop. When it goes from no load to full load, the speed will drop by 2%. This may sound counterintuitive, but it prevents generators from fighting over load by allowing operators to change the speeder spring tension to determine how much load each generator carries. The compensation rod cancels out the limiter dial's motion by moving this cam as the gates respond to changes. This mechanism is the oil dashpot, designed to slow the movement of the wicket gates. As the gate actuator responds, the compensation linkage causes this piston to move, creating oil pressure on a small plunger that neutralizes the movement of the flyballs. As oil flows through an orifice, the compensation dashpot allows the flyballs to gradually regain control. These Woodward governors are very advanced pieces of mechanical control technology. The spring tension controls power based on speed, while the limiter knob can precisely control power output. On the other side of the generator shaft, a belt drives an oil pump inside this compressed air storage tank. A bypass valve allows the pump to circulate oil when pressure is high, while the compressed air in the tank stabilizes pressure as supply and demand change. Outside the powerhouse is a dam which holds back 20 feet of water between the surface of the reservoir and the surface of the Mississippi River. Right now, the river's flow is only enough for the 4 operating generators, so the floodgates on the dam are closed. Inside this room are the hydraulic actuators for the floodgates on the dam. Similar to the governor mechanism, this hydraulic relay controls the floodgates.
So when I pull this down like this, it's closing anymore. Opens this valve. get from there.
As water from the dam enters the powerhouse, it passes through this screen to remove debris. On top of the powerhouse, we see the transformers, which increase to 2,300 volts from the generators for transmission. Back inside the powerhouse, beneath the transformers, is the control panel. Although this knob may not look too special, it actually controls a rare piece of machinery. On one of the generators, a belt drives the small DC generator, which may use weak permanent magnets for starting. The DC output goes into the alternator's rotor to create the magnetic field. To control the generator's output voltage, this rheostat is used to regulate the excitation system. Because permanent magnets cannot be adjusted, it's likely the rheostat controls the exciter's field current. Changing the exciter's field changes its output, which in turn changes the main alternator's field current and output voltage. Besides the unusual rheostat, there are synchronous lights, voltage gauges, breakers, and some electronic indicators. These control panels regulate the other two generators, which don't have mechanical governors. While in Brainerd, I also found this abandoned railroad power plant. I contacted the Northern Pacific Center and I was able to get a quick tour. There were likely steam turbines in this building, but now all that's left is a steam-powered air compressor. This power plant would have supplied utilities such as heating steam, compressed air, and of course electricity to the large shops of the Northern Pacific Railroad. In the back of the plant are the boilers. I was only allowed to peek through the door on my tour because of safety issues. Old power plants like this often had multiple boilers for redundancy since the power grid was not as well developed and people relied on these plants for district steam heating. I wanted to show you a picture of what this plant looked like when it was operational, but publishing a photograph from the Historical Society would cost $150. Few power plants still operate mechanical Woodward governors. I hope this video helped you understand how it's possible to control generators without modern computers, using only century-old technology. Here's more videos about hydropower and various other industrial machinery.